Okay, so let's go ahead and do this banked curve example. So in this example, we have a car that's going around a very sharp curve, a 50-meter radius curve, and it's a frozen road, and we're assuming here that it makes it frictionless. And so you might assume if you have a frictionless road, there's nothing you can do. You would just slide right off the road. But that's not the case, and we'll go ahead and show that in this problem here. So we have this car then, this is the view from behind, that's going along this banked curve, and the curve is banked to 20 degrees. Okay? And it's a frictionless road, so let's go ahead and identify the forces that are acting on the car here. Well, gravity, remember, is always at play. So gravity pulls downward with the force mg, and the normal force pushes back up from the road perpendicular to the surface with the normal force. And this is not to scale at all here, the lengths of those vectors, but that indicates their directions. And there is no friction at play here, so these are the only two forces acting on the car. The next thing to ask ourselves is there an acceleration? And yes, the car is going in a circular path, so it would be accelerating towards the center of the circle if it were going on a circular path. Okay? So the direction of acceleration right here would be towards the center of the circle. Okay? So let's go ahead and work this example here. So let's draw our free body diagram. So there's our y-axis and our x-axis. And we're choosing our x-axis to be pointing towards the center of the circle. So remember, the acceleration isn't down the slope, okay, because the car isn't sliding up and down the slope here. We're assuming it's staying as it goes around the curve. But there is the centripetal acceleration that's pointed towards the center of the circle. So this car is going in a circular path. It's going into the board here and then out of the board somewhere else. And so the center is somewhere off over to the right, not down that way. Okay? So let's put these forces on the free body diagram here. So we have gravity pulling down with a force of mg. The normal force pushes back up at some angle. And if this is a 20-degree angle here, then the normal force makes a 20-degree angle with the y-axis. So go ahead and think about that one for a little bit. But it is this angle between the normal force and the y-axis that's 20, not this angle here. Okay? The best way to see that is if you have a flat road. If the road is flat, this angle theta goes to 0, and the normal force points straight up. And so the normal force would make a 0-degree angle with the y-axis. Okay, so there's the setup. Now our x-forces for a centripetal force problem like this have to add up to the centripetal force, mv squared over r. And the y-forces add up to mass times y acceleration, which is 0. Okay? The car is not moving vertically in the y direction. Okay? So we need to apply these to our free body diagram. So let's start with the x components. Now, gravity points along the y-axis, the negative y-axis. So it has 0 x component. The only x component here comes from the normal force. And so the x component is this right here, which is also that there. And so it's opposite the 20-degree angle. So opposite means sine. So we have normal force times the sine of 20. And that equals mv squared over r. So for the y-forces, we want the y components of each of these. And the y component would be this. And that's adjacent to the 20-degree angle, so we use cosine. So we get n cosine of 20. For gravity, mg points downward in the negative y direction. So we get minus mg. And that has to equal 0. Okay? So this is an equation with only two unknowns, the normal force and velocity. So we don't really need to know what the normal force is. The question is about the velocity. So let's eliminate the normal force by solving this for n. So that gives us mg over cosine 20. We can plug that in over here, and that gives us mg sine 20 divided by cosine of 20 after plugging our normal force in there. And that equals mv squared over r. Okay, the masses cancel out. And we multiply both sides by r. Sine 20 over cosine 20 is tangent of 20. And we get the velocity is the square root of rg tangent of 20. Okay? So r is 50 meters, g is 9.8, times the tangent of 20, then take the square root, and you get the answer 13.4 meters per second. Okay? So any faster than that, and the car can't make this curve. The car is going to slide basically off the curve. Okay? Now, also, what this also means is if the velocity is any less than this, the car isn't even going to be able to stay on the bank here. The car is going to slide down to the inner part of the curve here. Okay? So, in other words, to make this work for a frictionless road like this, yeah, you can design it so that a car won't slide off if it's frictionless, but you have to have exactly the perfect speed, in this case 13.4 meters per second, to stay on the curve at all. Okay? So frictionless, that's why this is not a realistic problem. It's a frictionless situation. When you start to have a little bit of friction, even something as slippery as ice, you get, you're really not going to have a situation where you slide off to the inner part. Okay? But there will be a maximum speed beyond which you'll just slide off the curve.